Hello, this is Frazier Nyasulo. Let's talk Lab 7. Equilibrium constants for weak acid, weak base reactions. We've seen equilibrium constants quite a bit. It's just because they occur everywhere in chemistry. Among the more important ones are the ones related to weak acid, weak base. So let's see here. All right, so what are we doing in this lab? We are going to determine the equilibrium constants for these reactions down here. The ones I'm pointing to: acetic acid, ammonia, weak acid, weak base. And then the rest of them are also a combination of weak acid, weak base. The equilibrium, what is the equilibrium constant? You'll note that we don't do any strong acid, weak base, or weak base, strong acid. The reason is those have huge equilibrium constants, and we can't ordinarily determine them here. But for these here, we need to do some other procedure to determine the equilibrium constants. The reason is there is no direct or easy way to measure the quantities and come up with the numbers. So we do it indirectly. All right, so let's, in order to do so, we'll need to determine the Ka values, the Ka for these acids up here. That's acetic acid, the ammonium ion NH4 plus, and then for phosphoric acid we need Ka1, Ka2, and Ka3, and it turns out that with these we can determine the equilibrium constants for these reactions here. All right, let's talk about how you determine the Ka values. You've seen a little bit of this in the previous lab, but we're going to do it in a more direct way. The more accurate and more direct way, if you're doing it via pH, is to mix a weak acid and its conjugate base, and then use the Henderson-Hasselbalch equation. So if you look down here, pH is equal to pKa plus log A minus over HA. That's the Henderson-Hasselbalch equation. And then you apply it for the case at hand. So if we're doing with pKa1, then this is H3 and this is H2. These are dissolved in the same solution. So although the original Henderson-Hasselbalch's concentration, we can just go with moles because the two volumes are the same and then they cancel out. All right, so how do we do that? In our case, we'll take a test tube. We'll add an aliquot, non-molarity of the base, non-volume, so M times L is moles, and the acid, again, M times L, that's moles. So the acid down here, the base down there, up here, and then can do the arithmetic. All right, we'll know what the numbers up here. We'll take the log, and then if we measure the pH, you can solve for pKa1, and from that solve for for Ka. So really easy to do in our case. Test tube. Few milliliters of the acid, few milliliters of the base, maybe add an additional amount of water just to make sure that there's enough to submerge the pH electrode sufficiently. If you do this, when it comes to calibrating the pH meter, you're going to use pH 4 and pH 10. Make sure that after calibration you measure both pH standards and make sure those are coming out okay. Moving along, some definitions. These are easy and straightforward. Phosphoric acid, triprotic. And we start with the mother species, it's H3PO4. So the first ionization is Ka1, the second one is Ka2, and the third one is Ka3. And our reference to this is, for this one, we say it's Ka3 of H3PO4. So that's the acid ionization processes. How about the base? Each time you have a weak acid, the conjugate thing is actually a weak base. So here, if we start with PO4, which is the most basic, reacting with water to form HPO4 2- and hydroxide, that's KB1. And that will be the largest number in terms of comparing KB1, KB2, and KB3. Then the next one will be KB2. So you create here H, no H here to H1 here, and then the second one will be forming H2, so that's KB2, and then third one you'll be forming KB3. And KB1 is bigger than KB2, is bigger than KB3. In terms of the KW relationships, you want to note Ka1, which is a big number, well, bigger than the rest of them anyway, times KB3, which is a small one, is equal to KW. Big, small, KW. These are intermediate, so Ka2, Kb2 is equal to Kw, and then Ka3, which is the smallest one of the Kas, gotta multiply with the biggest one of the Kb's to go Kw. We need those expressions as we go forth. Okay, the ammonium ion, what does that do? Okay, the ammonium ion here, it's an acid, so it does its acid thing, forming the hydronium ion on the other side. Ammonia is a base, and you want to note this equation. You go from NH3 to NH4 plus, and you create hydroxide. That's a Kb expression. And these are linked by Ka times Kb is equal to Kw. Moving right along. All right, so now let's get to the meat of the lab. Let's process the equations. So how does it work? There is a mother equation that we're looking for. We're trying to find the equilibrium constant for that mother reaction. We're going to create baby reactions that add up to the mother reaction. And it turns out that via our measurements today, we'll know the K values for the baby reactions. And from that, we'll determine the Kb for the mother reaction. So, let's consider this reaction here. That is our mother reaction. H3PO4, 2 ammonias in this case, forming 2 ammonium pluses and HPO4 2-. Let's think about this. What's happening here? Oh yeah, it is an acid-base reaction. Yes, it is a weak acid, weak base. Okay. Now what we'll note here is that H3, that's the acid, goes all the way to H1. But that happens in steps. So we go H3 to H2 to H1. 2 steps. Whenever we're decreasing the H pluses, H3 to H1, that's an acid ionization. Let me say that again. Whenever you're going down in the number of H's, the ionizable protons, as you go from reactant to product side, that's a Ka, that's an acid behavior. The opposite of that, if you're increasing the H's, that's a Kb. So this process here gives you the hydronium ion. That's an acid. This process here, NH3 to NH2, gives you the hydroxide ion. That's a Kb. That's all you need to know. Okay. Base hydrolysis, that's what we have there. Acid ionization, in this case, this is a 2-step process. Let's go. Okay. Let's start with the ammonia. That's a base hydrolysis. NH3 to NH4, so I write NH3 to NH4 here. I write water there. And I could write 1 NH3, 1 water, 1 NH4 and 1 OH minus. But I write 2 of them because 2 of them are in the equation. But that's a Kb expression. Producing hydroxide, Kb. But because with it 2 and the 2 and the 2 and the 2, so we're going to go KB squared, but we want to write this in terms of the things that we're actually measuring. So I'll write it as KW over KA, not just simply KA, but KA of NH4 plus. And then we square it here because this equation is multiplied by 2. So you'll be seeing this equation quite a bit, the ammonia one. How about the acid? H3 in steps to H2. That's one step. H2 to H1, the first step. The first one, we write it as an acid ionization. Produces H3 there and H2PO4 minus. There it is. Call that by its right name, Ka1. How about this next step? That's Ka2. So this step here actually consists of Ka1 and Ka2. Moving along. Let's write the baby reactions and see if we can combine them into the mother reaction. Now, in writing these, wanna focus on what happens in the mother equation. So H3 tends to H4 in the mother equation, so there it is. We call that KB2. Here's Ka1 and here's Ka2. Well, if I just do that, I end up with things not canceling out. I end up with 2 OHs on the other side and 2 of these hydroniums on. There's one here, there's one there. Let's pick up a pen. Let's see if it will let me pick up a pen here. No. By now I should know how to do this. Should be in slide mode. Then it will allow me to pick up a pen. All right. Pointer options. All right. So, if I stopped here, the mother equation doesn't have hydronium, H3O plus, and 2 of these. Everything else seems to check out. So I'll need a way to get rid of them. Well, this is on the product side, so get rid of it, I'll write it on the reactant side. This is on the product side, get rid of it, I'll write it on the reactant side. And this and that give H2O. Well, that tends to be a KW reaction written backwards. And this is 2, 2, and 4. We're familiar with 1, 1, and 2. So this must be 1 over KW squared. Now, if I add up reactions 1, 2, 3, 4, they generate my net equation. And guess what? I have all the expressions here and have all the numbers for the right hand side. I can calculate Kc. Kc, which is equal to these here, and I have no way of determining those directly, at least at this point in time. I'll just multiply the entries on the right hand side, 1, 2, 3, 4, and whatever I get, put in the numbers, will be the equilibrium constants. Now, if I put these out and write them out and multiply them, the KWs always cancel. That gives you an indication that you're doing things correctly. So this says that this Kc, which is the reaction for the mother equation, is equal to Ka1 times Ka2 divided by Ka of NH4 plus squared. So in the lab, you'll know what this number is. You know what that number is. You know what this number is. So you can calculate what this number is. All right. Numbers. Gotta know what they mean. So let's derive a meaning. Well, weak base, weak acid, weak acid, weak base. Do these reactions go to completion? Well, we can look at the Kc value and get some idea, but let's do it quantitatively anyway. And this is how. We'll write the reaction in the balance equation for the mother reaction, and then we'll assume that we have stoichiometric amounts of reagents. It doesn't matter what you call them, but if because there's a 2 here and a 1 here, I'll call this 2 molar here and 1 molar here. That's what I mean by stoichiometric amounts. This could be 0.2 or 0.1. Really doesn't matter. So pick the simplest number. Well, 2 here, 1 here. All right. So, and we will say a reaction goes to completion if it goes by an extent of 99% towards the right-hand side. If that occurs, then 99% of this reacts, so the change is not 2 but 1.98, and 0.99 here, creating 1.98 and 0.99 there. Again, just following the stoichiometry of the reaction. And the equilibrium will leave 0.02, because 1.98 reacted, assuming 99%, and similarly here 0.01. You can get these numbers and calculate what I'll call a QC. QC. Well, I'll put in the numbers that I hypothesized up there, and I get a number that's 9.7 times 10 to the 5. That looks like a big number to me. That's an equilibrium constant. That's a big number. That suggests that maybe the reaction goes to completion. Well, let's check it out. What we're going to do in this checkout is to find out how it compares with the actual equilibrium constant. So, here's my QC. Here's my equilibrium constant that I just calculated. Yeah. QC is much smaller than KC. QC is much smaller than KC. Well, how would I get this QC to approach KC? Well, what I'll need to do is to assume a greater extent of the reaction. If I go 0.999 or 99.9% reaction, then this number increases, right? This number here will decrease, this number will decrease, this number increases, this number will increase. So the idea is, when I assume 99%, I get QC less than KC, then it means that the reaction is more than 99% done. Because in order to get QC to get to KC, I've got to allow for greater percentage reaction. So if QC is less than KC, the reaction is more than 99% complete. Inverse of that, if KC is less than QC, then we can say the reaction doesn't go 99%. It's some number less than that. So we can do this for all these reactions. Not only find the KC, but also find out if the reaction goes to completion. And that's what we're doing in this lab. So let me go back here. This that I'm showing up here happens to be the more challenging one. The rest of them involve fewer steps. Typically 3 reactions. So going back again here, you look at the mother reaction and go, I'm going from here to here. That's an acid dissociation. From here to here, that's a KB. Write the appropriate reactions for each one. Sometimes you've got to write it in 2 steps. Consider whether you need to multiply the whole equation by 2 or whatever it is. Consider base hydrolysis to cancel. The weak acid, the KW expression to cancel the OH or H3O plus that might occur in the system. Check that everything is right. Write all of these on the right hand side here in terms of the Ka values, right? So this is a Kb, so we write in terms of Ka. Do the arithmetic, come up with Kc. Think about whether Kc represents a complete reaction or not. So that's our lab today. Measurements are easy and straightforward. You can do these measurements 25 minutes max, and you spend the rest of the period figuring out all those expressions and checking if the Kc indicates a reaction as being complete or not. So in this case, looking at the procedure, this is acetic acid and then sodium acetate. The two of them will give you, Ka for acetic acid. Here's H3PO4 and H2, that will give you Ka1. H2 and H1, that will give you Ka2. H1 and no H, that will give you Ka3. Ammonium and ammonia, that will give you Ka for NH4. And then, of course, you're off to the races with the expressions. Have a good lab.